Hello, AP Calc BC. This is our work for after the exam. So this is for the juniors who are left. And so what we're going to be doing is the hyperbolic trig functions. These come from an old textbook. I'm pulling this from an old textbook that I had. These, you won't have to do a whole lot of justifying and writing things out like you did for the FRQs that we were doing to get ready for the AP exam. A lot of this is kind of chugging through things. Where the critical thinking comes in is using these trig identities and figuring out how to manipulate one form from the next. And then also understanding some of the calculus behind it with the derivatives and the integrals. But I would have to say that this is kind of the easier part of the calculus. It's just with functions that we've never worked with before. So what I'm going to do today is go through the basics behind some of these functions and some of their identities, and then do a few examples, and then your first assignment will come from the exercises at the end of this section. So the hyperbolic trig functions, kind of like the normal or our regular trig functions. Our regular trig functions are all based around sine and cosine, and you can take every single one of the normal trig functions and rewrite that in terms of sine and cosine. And with the hyperbolic trig functions, the same thing is true. And so for that reason, we're going to start off by talking about the hyperbolic sine and the hyperbolic cosine of u, or any general function or variable. So, and how we express that it's hyperbolic is we throw this h in there, right? And so you can think about this as cinch u or cos u, and that's actually how we say it, cinch u or cos u. And these are related to these functions involving e, or the exponential. The normal trig functions kind of are related to graphs of circles, and because these are hyperbolic, they're related to the graphs of hyperboles. So that's where some of these identities come from with the exponentials. I'm not going to get into too much of where they come from and how to derive them. A lot of this we're just going to be presenting you with the identities, and then the work is going to come from the algebra to switch back and forth from the identities. So for the hyperbolic sine of u, we could call that cinch u, and that's 1/2 e to the u minus e to the negative u, and then cos u is the only difference here is we have a plus sign in the middle. Okay, so two very similar identities, just that sign in the middle is different. So some people will also say, instead of saying cinch u, they'll say shine u. I've always just said cinch. So, but you can say whatever you like. Now, so where do these come from, and how can we see them graphically? Well, you know, cosine and sine are identified with the point x comma y on the unit circle x squared plus y squared equals 1. And so cos u and cinch u are identified on the unit hyperbola x squared minus y squared equals 1. And so if you want to check the points with the coordinates, you could just substitute these relationships, these identities that we were just given, right? So if we know the basic form of a hyperbola is x squared minus y squared equals 1, we could replace that. Well, let's associate x squared with cos squared and y squared with sinh squared. Similarly, with our normal trig functions, we would associate x with cosine and y with sine. And so then, well, if it's going to be cos and sinh, then we can throw in these identities that we just gave in the box up here. Okay, and so if I put those in and then square them, that equals 1, and then I simplify them. Okay, I run through the algebra and cancel out common terms, and yes, it really does work out. It really does equal 1. Okay, so that's kind of how we can prove that. So then you have this next statement here. You could say that x is cos u, which is 1/2 e to the u plus e to the negative u, and y is sinh u, which is 1/2 e to the u minus e to the negative u. So if we have that, we can see that u, or whatever variable you want to plug into your cos or sinh, or your domain of cos and sinh, is going to vary from negative infinity to positive infinity. Okay, so the domain of cos and sinh is from negative to positive infinity. And let's see. Now, this point Pxy describes the right-hand branch of the hyperbola, and that's going to come into effect later when we talk about which of these can be positive and which of these can be negative. E to the u is always positive, and e to the negative u is 1 over e to the u, which is also always positive. Okay, so if those are always positive, then cos u is always going to be positive for all real values of u. And so that point will always be to the right of the y-axis. Okay, and so then we can throw in the graphs of them here. And so you can see that if you were to graph the hyperbola, the xy of this point on the right will always be, if it's your x coordinate right here, and it's your cos, it'll always be positive. Okay, so then if we have that, then we can come up with a hyperbolic identity, which is just cos squared minus sinh squared is 1, right? And so this is kind of similar to our Pythagorean identity, sinh squared plus, or sine squared plus cosine squared is 1, except the sign difference, it's minus. Okay, so now if we have this, then we can go ahead and relate this to our other trig functions and come up with the remaining hyperbolic trig functions. So the hyperbolic tangent is going to be tanh, which is going to be sinh over cos, right? So similarly, normal tangent is sine over cosine, so we've got sinh over cos, and so you can just throw those identities, e to the u minus e to the negative u over e to the u plus e to the negative u. And then cotangent is the reciprocal of that, so we could call that cos u, which is cos u over sinh u. And then hyperbolic secant, that's going to be the reciprocal of cos, and so we would say sesh, so that'll be 1 over cos u, which turns into 2 over e to the u plus e to the negative u. And then the same thing for hyperbolic cosecant, we'll get that from sinh, so cosesh, I guess that's the best way you could say that, is cosesh. That's going to be 1 over sinh, which is 2 over e to the u minus e to the negative u. All right, so we were able to come up with our 6 hyperbolic trig functions, and what we can do is we can even come up with some other Pythagorean identities. And so similarly in the normal, with the normal trig functions, we had I1 a tan and a second, or 1 plus tangent squared is secant squared. Well, we would have 1 minus tangent squared is sesh squared, and then we could say cos squared minus 1 is cosesh squared, so that's another one. And if we want to do cos and sinh, add them together without squaring them, we can get cos plus sinh is e to the u, and then cos minus sinh is e to the negative u. Okay, so we've got some identities there that will help us with some of the algebra. Now, if e to the negative u is positive, then the equation cos minus sinh equals e to the negative u, that's going to show that cos is always greater than sinh. And so for large positive values of u, though, e to the negative u is going to be small, and then cos u is approximately equal to sinh u. Okay? Now, comparing some of these trig functions, so a few facts maybe that are worth memorizing or having notes of: cos of 0 is 1 and sinh of 0 is 0. So with the hyperbolic trig functions, they all have the hyperbolic trig functions have the same values at 0 that the corresponding trig functions would have. So that's nice and easy and helpful to remember. And then even just how the regular cosine function is an even function, the hyperbolic trig function, the hyperbolic cosine function, or cos, is also an even function. And so that has to do with the fact that it's always positive always on the right side of the y-axis. So cosh of negative x, we could run through the whole identity process. That's going to be the same thing as cosh of positive x, right? And we've got this identity in the middle to prove that. So we've got these graphs here. And so these graphs just show the graphs of the 6 hyperbolic trig functions. So we've got y equals cosh x, which looks like this parabola right here. Just highlight that. And then y equals sinh x, which looks like maybe this cubic function here. So you can see how cosh is an even function and then sinh is an odd function. And then we can graph coth x, y equals coth x. So that's going to be this upper curve here and this lower curve here. And then y equals tanh x will be this one that exists between y equals -1 and y equals 1, right? And then you can compare y equals cosh x. Well, the reciprocal function of that is sech x, y equals sech x. And so you can see how it just looks like the flipped version, but expanded, and that makes sense. It never ends up equaling 1. That makes sense because you have 1 in your denominator. I guess the only time it does equal 1 is when you're at 0, right? And then we can compare y equals sinh x to y equals cosec x, which is the reciprocal of that. Okay, so, and here's kind of the explanation why the cinch function is odd, right? If you do cinch of negative x and plug negative x in and work through that, you're going to end up getting negative cinch x, okay? Now, a few basic facts that will help us in understanding some of the values that we're going to have to figure out. Let's see. So something important to note, the trig functions are periodic, but the hyperbolic functions are not, okay? So our ranges are going to be a little different. So you know sine x oscillates between -1 and +1, but sinh x is going to increase steadily from -infinity to +infinity. So it doesn't oscillate, but continually increases. And cosine of x also oscillates, but cosh x is going to go from +infinity to +1 and then back to +infinity. And then the absolute value of secant x is never less than 1. And then sech x, well, it's never greater than 1 and it's always positive. Tangent x will vary between -infinity to +infinity, but on the flip side, tanh x, the hyperbolic version, is going to vary from -1 to +1, okay? So we can't say anything really specific about the behavior of the circular functions of our normal trig functions because they just keep going around and around in the circle, and their values just keep oscillating and going back and forth. But the hyperbolic functions, they do behave like the model functions e to the x over 2 and e to the -x over 2. So when the values get really, really large, cosh x and sinh x are both going to look like 1/2 e to the x. If they're large and positive, tanh x and coth x both look like 1. And then sech and cosec are both going to turn into 0. And then if the values get really, really negative, they're going to turn into 1/2 e to the -x, -1, and 0 respectively. Okay? And then just like we have a whole bunch of identities with our normal trig functions, we can also have these identities with our hyperbolic trig functions. So here's our sum property. So sinh x plus y, that'll turn into sinh x cosh y plus cosh x sinh y. And then cosh x plus y is going to be cosh x cosh y sinh x sinh y, right? So cosh cosh, sinh, right? And both of them have x and y. But then when you do it with sinh, it flips. So then we also have some double angles. Sinh 2x is 2 sinh x cosh x, and cosh 2x is going to be cosh squared plus sinh squared. And then we talked about this this Pythagorean identity 1 equals cos squared minus sinh squared, and then we can kind of rework some of what we have from the double angle identities and get cos 2x plus 1 is 2 cos squared x, and then we can kind of flip things around there, right, and subtract 1, and we would get cos 2x minus 1 is 2 sinh squared x, and also cos 2x is 2 sinh squared x plus 1. So I'm just moving the 1 over to the other side to get that second identity. And then if we want to divide everything by 2, well, if we were to take cos 2u plus 1 divided by 2, that gives us cos squared, and then cos 2u minus 1 divided by 2 will give us sinh squared. So at the end, these are all just identities that we're going to be using in our algebra to kind of roll through some of this stuff here. Now, what I'd like to do is go through some classwork examples, and then let's see, together we'll do 2 and 8 from this, and then I'll cut you loose to do an assignment on your own, okay? So let's see, we'll do number 2, and then we'll do number 8 together, okay? So let's see, if we scroll down here, so for number 2, we are given that cos u is 17 over 15 and u is positive. And so what we have to do is give the values of the other 5 hyperbolic trig functions. Okay? So, let's see. Well, the first thing that I want to do is kind of lay out where some of these things are coming from, or how some of these things work with each other. If I think about my Pythagorean identity, I have cos squared u minus sinh squared u is 1. And they just told me that cos u is 17 over 15, so I'll say this is 17 over 15, the whole thing squared, minus sinh squared u equals 1, right? So then I could say, well, then this is going to turn into 289 over 225 minus sinh squared u, which is 1. So then I could get my sinh squared by itself. So let's see. So a negative sinh squared u is going to be 1 minus 289 over 225. Or we can say 225 over 225 minus 289 over 225. So then, and if we reverse the sign, we can say a positive sinh squared u is going to equal 289 minus 225 over 225, right? And so then this is going to turn into 64 over 225. So then we know that sinh u is going to be positive or negative 8 over 15. And yeah. So there we go. We found sinh, and they told us that, let's see, cos is already 17 over 15, and then tanh, remember, is going to be sinh over cos, so that's going to be 8 over 15 times 15 over 17, which is going to turn into 15 over 17. Right, so let's see. So this is one answer. This is one answer. Okay? And then we just do our reciprocal functions. So Cosec U is going to be the reciprocal of sinh, so that'll be plus or minus 15 over 8. And sec U is going to be the reciprocal of cosh, so that'll be 15 over 17. And then coth U is going to be the reciprocal of the tangent, so that'll be 17. Did I do that right? Oh, I think I made a mistake up here. Sinh is 8 over 15, right? Oh, that's the problem. I had it set up right and I just wrote the wrong number. Right. So then this should be 8 over 17. That's much better. Right. So then coth U is going to be, and actually this should be a plus or minus too. Coth U will be plus or minus 17 over 8. Okay. So these are our 5 other hyperbolic trig functions, right? And so you'll have to do problems like that for the first few problems in the assignment here. So now let's take a look at number 8. So if we go back up to the top to see what number 8 was. So for number 8, they want you to rewrite the expression in terms of exponentials and write the final results as simply as you can, okay? So in terms of exponential, so that means they want it with all e's as simply as possible. And so what they give us for number 8 is cinch of, and the argument of this is 2 natural log x, okay? Well, the argument of cinch here is going to be 2 natural log x, so then that means my exponent on my e's is also going to be 2 natural log x. So I could rewrite this with the identity that I was given for cinch and say that this is the same thing as 1/2 e to the 2 natural log x minus e to the negative 2 natural log x. Okay, and then what I think I'm going to do is these 2's that are in front of these natural logs, I'm going to throw them over and make them the exponents on those x's. So then this will turn into 1/2 e to the natural log x squared minus e to the natural log 1 over x squared. And then, well, if I have e to the natural log of something, the e and the natural log just cancel, and so then this becomes x squared minus 1 over x squared, right? And so then if we distribute our 1/2 through, we're going to have x squared over 2 minus 1 over 2x squared, and we can simplify that and get things over one denominator, and so I'll have x to the 4th minus 1 over 2x squared, okay? And so this would be my final answer for number 8. So hopefully that gives you a hint about how to do some of the other problems in the assignment, and you can go ahead and try the first assignment.